Welcome to this presentation. This is Daniel Casini, and today I'm going to present latency analysis of I/O virtualization techniques in hypervisor-based real-time systems, a joint work with Alessandro Biondi, Giorgiomaria, Cicero, and Giorgio Buttazzo.
Let's start from the motivations of this work. Modern real-time applications are becoming increasingly complex due to multiple sources of unpredictability. For example, think to the contention they can experience in accessing shared memories and I/O devices. These issues give rise to the need for software-based solutions to mitigate them. And that's here that hypervisors come into the game, but this is at the expense of additional complexities such as a more complicated handling of interruptions, hypercalls, and the need for virtualizing I/O devices. This is especially relevant in autonomous driving settings, where tasks tightly interact with I/O devices. In this work, we propose a worst-case analysis of I/O virtualization techniques, but although our research specifically targets I/O virtualization, it has also to account for all the other complexities introduced by a hypervisor-based system, as they all have a substantial effect on the application timing behavior. In this work, we considered three I/O virtualization scenarios: pass-through I/O and two variants of I/O para-virtualization. For each of them, we studied four different metrics: the response time of tasks and interrupt service routines, the input data delivery latency, the output data delivery latency, and the input processing latency. And we considered two types of I/O: synchronous I/O and asynchronous I/O. Let's start with I/O virtualization with pass-through. In this approach, each application running in a virtual machine interacts by means of the I/O device driver with an exclusively allocated I/O device. This approach is simple, it has a reduced latency, but unfortunately it doesn't allow device sharing. For this reason, we introduced two other approaches based on I/O para-virtualization. In I/O para-virtualization, tasks invoking I/O operations are aware of being virtualized by an hypervisor. And to invoke I/O operations, they call a specific API provided by the hypervisor. For example, you can see here these I/O send and I/O receive functions. Next, we consider two different scenarios. In the first one, I/O buffers are allocated in the memory space of the hypervisor, and each VM communicates by writing and reading data to the hypervisor memory space by means of a hypervisor-specific API. An inter-domain communication mechanism provides such data to the I/O VM, which is a special-purpose VM in charge of accessing the actual I/O devices using pass-through communication. The I/O VM implements the I/O manager that enqueues different requests and dispatches them to the I/O driver. Let's have a closer look to the I/O manager. The I/O manager implements the scheduling logic for I/O requests coming from different VMs. Here we have two queues, one for input, one for output, for each pair of virtual machine and device. Each queue is managed in FIFO order. There is also an inter-queue arbitration, which is implementing round robin. In our analysis, the corresponding worst-case delays have been analytically bounded. With respect to pass-through I/O, I/O para-virtualization has the advantage of allowing device sharing, but it has also some drawbacks. First, we need to copy data from the private memory of the producer VM to the buffers allocated in the hypervisor memory. And second, we need to do this using an hypercall, and this may cause additional delays. Why? Because hypercalls execute at a higher priority with respect to the one of the requesting task, and this may give rise to priority inversion blocking. For these reasons, we also considered a second scenario, in which each VM has a dedicated buffer allocated in a shared portion of memory, and each buffer can be accessed only by the related VM and the I/O dispatching VM. This approach has some advantages with respect to the previous one. First, less copies are needed. And second, no hypercall is needed to copy data in shared memory, reducing the priority inversion blocking. To analyze I/O virtualization, we needed a fine-grained modeling of the system. Here I will provide the most relevant parts of our system model. We start with virtual machines. We modeled the virtual machines and we considered a partitioning hypervisor where each virtual machine is statically assigned to a set of cores in an exclusive way. Then we modeled tasks. Each task is statically assigned to a processor and executes under fixed priority scheduling. Each task is characterized by an arrival curve, which upper bounds the number of release events in a time window, a deadline, a fixed priority, a virtual machine, a set of I/O devices, a worst-case execution time, and some other parameters. We also modeled interrupt service routines. They are modeled similarly to tasks with some restrictions. For example, ESRs have higher priorities with respect to tasks, and they are assigned to two categories: VM-level ESRs and hypervisor-level ESRs. Hypervisor-level ESRs handle hypervisor-specific events or the first handling of ESRs to be redirected towards a VM. This creates a chain of computational activities, an hypervisor-level ESR and a VM-level ESR, that is important to be considered when deriving the worst-case analysis. Then we modeled non-interruptible regions where preemptions and interruptions are disabled. This is modeled with a mechanism based on a system ceiling. Depending on the value of the system ceiling, preemptions are disabled, or only hypervisor-level ESRs can preempt, or preemption is enabled. We also modeled hypercalls, which have been modeled with a priority elevation mechanism. So a task starts executing with its priority, then the priority is elevated to a higher priority when executing the hypercall, and upon termination of the hypercall, the original priority is restored to allow the task continue the execution. Next, we modeled I/O requests, which are performed by tasks to devices. They are characterized by a type, input or output, and the size. And finally, we modeled device events to model the arrival of data from the external environment to a device. Each I/O virtualization scenario is modeled with a set of rules to explicitly define the system behavior when a specific I/O virtualization technique is used. Here we have an example from our paper, and describing I/O virtualization techniques with rules is useful to reference them in the proofs of theoretical bounds. The analysis proposed in this paper builds upon compositional performance analysis. In our analysis, arrival curves for dependent tasks and ESRs are derived from the arrival curves of their predecessors by means of release jitter. This is needed for bounding latencies involving chains of computational activities. For example, a hypervisor-level ESR that triggers a VM-level ESR that in turn triggers a synchronous I/O task. Latencies have been bounded both with purely compositional techniques based on compositional performance analysis, and we also proposed more accurate holistic techniques. Here there is an example of a formula, but you can find all the details in our paper. The worst-case delay due to the I/O manager, which employs a FIFO plus round-robin scheduler, has been bounded with a multi-set approach. Again, you can refer to the paper for all the details. Now let me describe the latency metrics that we bounded in this paper. The first one is the input data delivery latency, or IDDL, that spans from when the data is delivered to the I/O device to when it becomes available to a target VM. Let's take a look to this with a timeline. First, the data arrives at the device. Then there is a chain of computational activities, a data copy, an hypervisor level ESR, a VM level ESR. Possibly, depending on the I/O virtualization technique, there may be an interaction with the I/O manager, and then the data arrives at the VM. This is the IDDL. Then, it may be relevant also to consider for the time required by a task to sample the data and to process the data. In this case, we can consider the IPL, input processing latency, that extends the IDDL to also include the time required by consumer task to process the data. These computational activities are subject to interference due to tasks, ESRs, and other I/O requests, and this is considered in our worst-case analysis. Then, we may want also to consider for delays in the opposite direction, so from the VM to the I/O device, and in this case we can consider the output data delivery latency, or ODDL, that spans from when the data is sent by a VM to when it arrives at the I/O device. Again, let's take a look to the timeline to clarify this latency. We start from when the data is produced by a task running in a VM. Then there may be a data copy, an interaction with the I/O manager, a chain of an hypervisor level ESR followed by a VM level ESR, and then the data arrives at the device. And so this is the ODDL. An extensive experimental study has been carried out to evaluate the worst-case performance of the latency bounds for the 3 I/O virtualization techniques considered in this work. We considered a realistic setup with 3 virtual machines, 1 running a real-time operating system and 2 running a feature-rich OS. The model parameters expressing the time required to copy data from a device to memory have been measured from an actual platform, the Zinc Ultrascale Plus MPSoC, and we monitored in our experiments the worst-case delays provided by the analysis for 2 tasks, the LiDAR task and the CAN task, whose parameters had been taken from the Water 2019 Industrial Challenge proposed by Bosch. We also generated synthetically additional interfering workload. Now let's have a look to some results for pass-through I/O and in particular for the CAN task. Here we are measuring the ODDL and we are decomposing it into latency to copy data and virtualization latency. Furthermore, we consider 2 different bounds, the purely compositional one and the holistic bound. Different groups of bars are reported to target different relevant cases, for example, the presence of interference, the absence of interference, the case in which all the ESRs related to I/O have the same priority, and the case in which those related to the LiDAR task and the CAN task have a higher priority, and cases with and without non-interruptible regions. From PTS1 in the chart, we can see that without interference we get very tight bounds. We can also see by comparing PTS4 and PTS5 with PTS2 and PTS3 that ESR priorities play an important role for the virtualization latency. And finally, by comparing blue bars with green bars, we can notice that the holistic bound is more accurate than the compositional one. Other trade-offs can be evaluated in the case of I/O para-virtualization, In this slide, we are targeting the case in which memory buffers are allocated in a shared portion of memory. And when dealing with I/O para-virtualization, we can extract from the ODDL also the time required by the I/O manager, that is named here I/O manager latency. And we can see that the I/O latency due to the I/O manager plays an important role in determining the overall ODDL. We also compared I/O para-virtualization in the case in which memory buffers are allocated in the hypervisor memory, scenario 1, with the case in which memory buffers are in a shared portion of memory, scenario 2. In this chart, the comparison is done with respect to the EDDL, while varying the maximum size of an I/O request, and we can see that scenario 2 is performing better than scenario 1. Finally, we compared synchronous I/O with asynchronous I/O, showing that synchronous I/O performs better than asynchronous I/O in terms of input processing latency. In conclusion, we showed that deriving I/O latency bounds for complex virtualized systems is possible with a fine-grained modeling. We proposed a worst-case analysis that also allows for a design space exploration of the system parameters to meet timing requirements. And we showed several trade-offs in our experimentation. Currently, we are implementing the proposed mechanisms in the Clay Hypervisor and using the Xilinx Ultrascale Plus SoC. And in the future, it would be interesting to derive tools for the design space exploration of the system parameters using this analysis.
Thank you. If there is any question, feel free to ask.